Okay, let's take a look at this simulation of our stationary wave in a closed tube. So for example, this is a closed tube, so there's a closed end here, so this is an open end. So let's just say there's a stationary waveform. So assuming, let's just say I have a incident wave, so this incident wave will travel through the opening and reflect off the closed end, right? So the incident wave and the reflected wave will superpose to form something called a stationary wave. So at this end is your node. At this end will be your antinode. Why is this end a node? It's due to the fact that there's a destructive interference here. So that's one way of saying. Because why? Because incident wave, when you reflect, right, there's a phase shift of pi radian. So means when the incident wave is right here, is a crest. So when you get reflected, become a trough. So the crest add on with the trough, right, to form a node point. So at the open end, definitely must be a antinode. Okay, so based on this simulation, so this is 1/4 of a wavelength. Right. Okay, let's take a look at the second stationary wave that can be formed in a closed tube. So for example here, so this is your so-called third harmonic, but don't need to memorize. So looking at this, here is a node, here is an antinode, here is a node, here is an antinode. So how many wavelength is this? So from here all the way to here is half a wavelength. From here to the open end of the tube, right, is 1/4 of wavelength. So means the total wavelength of this stationary wave, right, will be about 3/4 wavelength. Okay, so now we go to the last harmonic, the fifth harmonic. Okay, so based on the fifth harmonic, this must be a node. This will be an antinode. So what is the total wavelength? So from here all the way to here is one wavelength. From here to here, right, is 1/4 wavelength. So in total there will be about 1/4 of a wavelength. So that is how we actually calculate the wavelength of a stationary wave in a closed tube.